I guess we can start now. For the last several lectures, we have started to look into how the flow of control is happening in a, let's say, in a programming language, and what type of concepts, paradigms, or maybe small unifying concepts are there that actually is shared between perhaps different paradigms, as well as specific to some of the programming languages paradigms. So we started with expressions and statements, and then we kind of took a sidetrack to exceptions, where when an unexpected thing happens, what happens to your flow of control. And then now today what we are going to do is we are going to talk about what happens with units of code that we might have. And we know that as a common concept, procedures or functions or units of code that does certain things, or that are designed to do certain things or implement certain semantics, are common to almost all programming language paradigms. So the idea then is, how do we actually, what are the common concepts in these? And today we are going to cover that, and we are going to cover it in with a similar approach to expressions and statements. So let me see. So a function is similar to an expression, has no side effect inside, and returns a value. And a call to a function is going to be like an expression. So this means that with this kind of classification or definition, we associate these blocks of code that could be reused and whatever will have no side effect when they are called, right? And then they just return a value which can be part of an expression. And a function call in this case happens in an expression, and we know that an expression can be just a single function call in this case, or a composite function calls, and so forth, right? So this is the definition, one approach to actually define a function. And this will be probably some of the paradigms will follow this definition strictly, because again, the approach that we have seen with expressions, that if you assume this, that function doesn't have a side effect and just returns a value, then you can actually unify this concept with expressions easily, or use within an expression easily. The alternative is also, of course, a procedure. A procedure in this case similar to, or let's say, as a if we made a function something similar to, or defined function as a as an expression, or as a block of code that could be used in an expression, then we can make the same definition or similar definition for procedure to have a statement counterpart. Expression will be a function, or functions will be for expressions, and procedures will be for statements. So in this case, we assume that procedure has a side effect, like we actually did when we defined statements. Statements would have a side effect. So the reason that we will call a procedure is like a reason that we call a statement, to affect the current state of the program and change it so that something, whatever the programmer's intended semantic is, it is realized. And procedures are evaluated or executed, not evaluated, functions will be evaluated. We are going to make the distinction. When we call a function like an expression, functions will be evaluated, whereas when we call a procedure like a statement or a procedure will be executed for this side effect that we want to have. So if we have a procedure that doesn't have a side effect and doesn't return a value, so this is doing nothing. So we are smart people, programmers or computer engineers or scientists are smart people, will not write a code that doesn't do anything. All right. So usually, and in this case, a procedure call will be similar to a statement. So a single statement, a procedure call will be a statement. Of course, this is a good, so theoretically, this is very good. This is very easy to follow, right? So you have a function, an expression, they are, a function serves as an expression, and a procedure serves as a statement in terms of flow of control. So this is good, but of course, in real life, nobody actually we make exceptions, and in most languages, people do this, mix this up. So for example, C and C++ doesn't have limitations or doesn't actually distinguish explicitly what a function and a procedure is. A function with a void return type can be considered as a procedure, and also a procedure function, even with a return type, can do side effects. So some, as I said, but you can also make it side effect free as well. So you can C type of languages or C and its variants actually doesn't enforce this definition. Some languages will actually enforce this specifically. So when they enforce it, for example, a function will never be able to actually cause a side effect and return a value, whereas a procedure will never return a value. Act as a call to a procedure will be like a statement that enforces a certain state change. Of course, semantically, a state change may not be obviously, let's say, or explicitly enforced, and you cannot say, for example, from a compiler's perspective, either on runtime or maybe at runtime you can say it, but conceptually you cannot say, okay, hey, there is a procedure here, it doesn't do anything. It doesn't do any state change, and by definition it doesn't return anything. So this is not useful. This is programmer's intention. It can actually, programmers can do that type of a thing if they want to. Probably meaningless, but anyway. But a function, you can enforce that. Within a function definition, you can first of all enforce a return value. This is clear. As well as you can also enforce that there is no state change. So if you don't, for example, allow a global variable, a definition of a global variable, and some sort of, let's say, call by reference type of a thing, and then you actually prevent it as a language, you can easily prevent side effect free function. Prevent functions to have side effects by restricting things. Of course, restrictions mean other things and non-flexible. You won't have flexibility perhaps, but with the cost of actually this definition, And then when you enforce this definition, reliability would be probably better compared to, let's say, the alternative that functions can be procedures, procedures can be functions, and those type of things. So this is the concept. Now let's look at the syntax of a procedure or function. From now on, we are going to treat these functions and procedures as if they are the same. So there will be a body of a function or a procedure, and there will be a specification interface. So a function will have a name, a procedure will have a name. If it is a function, it will have a return type, and there will be some parameters, names and including names and types that specifies the interface to this particular function. There is an example here in C style code. You have a function definition that has the name. This is the interface part. And then you have the parameters, including names and types. And then you have probably a return value that is actually related with the body at some point. All right. So some languages, for example, may actually do a declaration of this interface first. This specify this interface in a separate declaration, and this can be forced or it can be optional depending on the language. But many languages will do this so that you actually have a way to declare your specification interface, and then perhaps at some point you implement that with implementing meaning you specify the body of the function. All right, so or a procedure. This is a syntax, the general syntax that people use for this type of things. Of course, this is not supposed to be always done this way. For example, in some languages, the specification interface could be something like this. For example, F, this is a made up thing, but this is not very, let's say, strange to, for example, to functional programming languages. So you define an F and you define, for example, a type, perhaps, let's say, integer for this function. It's going to be, let's do this for this particular function. And then we can do another one maybe for something else. So for example, this could be an interface specification for this function in a like a Haskell way or ML functional programming language. So you can see that a C style thing will have, let's say, this type of a thing, declaration where you expect a type of the return type of the function, a name, and then within parentheses, perhaps sometimes in C, for example, this Y is optional, but the type of the argument. So if you had another one, for example, some other function, let's say G, okay, this is not what I wanted to do, of course. So let's erase this part. So another function similar to this one could be something like this. This is, you can see that this is actually very similar to what mathematicians will do when they define functions. So this is going towards like the kind of making your declarations one-to-one mapping between, let's say, theoretical math. And once you know math, right, so you can actually program a lot of things easily with this approach. So this is usually one of the strengths of functional programming languages. So maybe your function, this new function, takes multiple arguments, like, for example, an integer and maybe let's say a double, and then returns another type, maybe let's say I don't know, something, whatever it is. So This could be for a 2 arguments as an input to a function, and then 1 output, whatever the type is. Of course, this is just a declaration, specification interface, and then you have to have at some point somewhere your body of the function. The actual semantic that this specific function is going to interface implement this interface of this function is going to implement will be in the body, right? Now then let's look at actually how the flow of control might happen, or what type of options we have to change the control, the flow of control, what gets executed when I call a function or a procedure. So the simple definition, there are several definitions here. This is a place where I call a function. All right. So and the place where we call the function is called the caller, obvious. And the specific function that has been called is the callee, the function that is called by caller. Now, in this particular case, I am kind of treating this function, not a function, but as a statement. This is not a, as you can see, this thing is not specifically, this is like a statement. Of course, this could have been, let's say, something else. So it could be also an expression, but the expression value is not actually used in any way. So it has to be part of a statement, perhaps, or of another function call. But doesn't matter. So don't take that for the time being, or don't pay attention to that as right now. So the caller calls a function. Of course, there will be, so this has to be following somehow or matching the interface definition or the interface specification of that function. And then the question is going to be, how do we go from, let's say, you execute this statement, and then you execute this statement, and then you are going to execute perhaps this statement. Now the question is, in this order, this is a simple let's say, imperative approach, right? So even in this order, the question is, how do we actually go from this caller to callee? When this happens, this control is switched to here, there are several things happening at the same time. First of all, the first thing is we have parameters that we actually pass to the function. How does this happen? What type of options do we have in this parameter passing? And then once that is actually, and then how is that, let's say, handled here when I actually come to, let's say, the first executable, let's say, statement in this thing, let's say this guy here. How do I actually go from this caller to callee and pass this to CPU so that the continuity happens? So there is no, I mean, these are in the same context, caller and the callee is within the same context, and they are part of a semantic that the programmer is trying to implement, right? So this has to be seamless. This transition from caller to callee should be seamless. And what are the options do we have here? What options do we have? What do we do during this transition? And of course, at the end, there will be an exit from this callee, and how that particular exit happens. And if it is returning a value, how do we return how we get that value? Let's look into that a little bit. So whatever, there are some very, very common concepts that has been used here. So the control is transferred from caller to callee at a procedure call or a function call. The transfer at some point it's transferred back to the caller when execution reaches the end of the body of the callee, and then you can also, you don't need to actually go to the end of it. For example, in this case, you can do an early return, right? So this is a possibility. Now, we need to, before we go into a little bit the details of how this going into the function, passing the control from caller to callee, and then from back to callee to caller, we need to a little bit understand the environment where these things are going to happen, and it will be seamless. We have thought about this quite a bit from time to time when we discuss variables, but let's review that a little bit again. So the environment is actually an environment with respect to, or is considered the memory, is the bound variables or bound memory to names. And for the time being, we are going to consider only the variables, but this could be also including function names and other things as well, functions and other things as other names. So names are bound to some memory, and we and of course some attributes as well. Those 6 attributes that we discussed, including the memory. So the environment of a programming of a program is usually, as you see it here, this is the memory environment where the binding happens. This is the memory part of the variables and other things. So we have the static global area, which is set at compile time or load time, and it doesn't change. And then we have the stack area. This is the stack area is used by the runtime system during flow of control, which automatically allocate spaces for local variables, procedures, parameters of procedures, and so forth. And this is under the control of the runtime system. And then we have heap. This is the manually allocated spaces. The allocation and deallocation in terms of the need for a heap is under the control of the programmer. But as we discussed the other time, the management of this thing could be done perhaps explicitly or implicitly explicitly by the programmer, or maybe implicitly some of the, let's say, the details of how the heap is managed and so forth can be handled by the runtime system. But heap is a memory that is in the control. The control of the heap is the programmer. And this is clear. And then what usually happens is that depending on the operating system and other things, there is a fixed amount of space that is allocated to a program usually, and this space has certain parts usually that actually grows. Let's say stack grows this way and heap grows this way, and then at some point, let's say you run out of memory. Most runtime systems makes this easier. I mean, to make the control easier, they actually will define a certain size for a stack at the very beginning. At the very beginning, they will define a certain size and certain size for heap as well. So this unallocated space is not going to be conceptually, it will be something like this, but usually stack size and heap size will be fixed. So therefore, the boundary, for example, might be here. There will be boundary, and this boundary, this part is going to be reserved for stack, and this part will be reserved for heap. So these are practical issues that you would see. So sometimes when you actually compile a program, you may need to actually specifically, for example, decide how much stack you are going to need. So by default, the stack size might be, let's say, I don't know, 100 megabytes, and you may want to actually have more of that depending on, again, your program's need. Okay, this is the environment. So these stack and heap is, as we know, are used for dynamic binding. One is again automatically, and the other one is per programmer's request. So, and then we have this definition of, or the concept of activation records. An activation record, if you remember, the memory allocated for local objects of a block. So this is a the local objects of a block of code. So we have a block of code here. You can see this is one block, and there is another block here. This is the outer block, and there is another block of code here. So there are 3 blocks of code here. So if this is a single file, this is the outer block, this is the one inner block, and there is another inner block here. So what happens is that when this is what usually happens, right? So when you enter a block, activation record is allocated. And when you exit from the inner block to the surrounding block, activation record is released. So this activation record, again, has only the local objects of a block. So you can see that this X is the global block. So there is a block there. This is global. And this is at the, if we are assuming that the stack is growing this way, this is this X here. This is this guy. All right. Now, when I actually, let's say, go to the second block, in this case, there is no function called here, but think about this as this procedural languages or imperative languages will actually define it mostly this way. So there is another block and a block here. This is this guy here. This block has this activation record here. This has to be the activation record for this one. These are the local variables. Memory allocated for the local objects. So X and Y here, you can see these are the ones. Now, if I am here, this will be the stack that I have. So if I am actually exiting this green block, somehow what will happen is that after the exiting of this green block, this particular, these X and Y, the last Y and then X will be released. There are some other things here. This area has some other things. This is related to stack is not just used for local variable or local object keeping. It has also things like, for example, if this was a function, this block was a function call, the parameter passing is going to have some of these spaces will have something about parameter passing, as well as the return address of where the caller where the caller actually called that function, the callee, right? So there are some other things that will happen in between. Okay, so now when you actually move one forward, of course, let's say when you get into this part of the thing, then you'll have this as your now activation record for this particular block here. So this is one activation record for, so this is the global activation record. This is the activation record for this block, this first block, and then this is for the second block. Now, the non-local variables in this case can easily be actually retrieved from the surrounding blocks by just going up to the stack. So you are actually trying to find, let's say, if you have I equals or I assignment x divided by 2. For evaluating this particular expression, you have to have x and 2. 2 is a literal, so no problem there. X is a variable. You need to find where the x is, and you can do that easily, perhaps by looking at your stack from top to bottom. Top to bottom. This is inverted here, but anyway. So you go up or top to bottom. The top of the stack is here. So you go top to bottom, and this is the bottom of the stack, and find the x. And in this case, you are going to find this x as your answer. All right, so you can see that this type of a very simple implementation enforces these, let's say, this static scoping, for example, that we had in mind, and so forth. And if you have, for procedures, they are the same, actually, like blocks. But in procedures, there will be some additional stuff, of course, as parameters. In this case, I don't have any parameters for these functions, or for these functions or procedures, whatever they are. They are actually procedures because there is no return value or a specific return statement indicated here. Perhaps it may say that, okay, the last expression that I have is a return value, but it doesn't say, oh no, there is no return value here anyway. So you can see that if I start from the main function, this x is going to be at the top of the stack or the bottom of the stack, because this is the first thing that will be actually declared. And when I go in runtime to a, at runtime, this will be initialized, and then a will be called. When I call a, I have x and y defined, and it will call b. You can see here, when I call b, then I is defined. Global variable, x is a global variable in the defining environment. This is clear. And I is a local variable. And for x and y, I need to have the information. I should be able to actually access this x and y, and this is how we do it. And then when we okay, let's see. All right. So you can see that there is no direct access to the local variables in the calling environment. So in this environment, I cannot actually, I need to communicate if I want to, let's say, access this guy here. So, okay, I made a mistake, sorry about this. So if I am calling B, B can only access I, its local variable, with the scoping, static scoping in mind. I was describing you the dynamic scoping in a few minutes ago. And X is going to be only accessing this from the defining environment, the global environment. So X, this is not reachable. This guy is not reachable by this one. If you want to have this reachable, you either change your mechanism for, of course, for scoping, which is very dangerous. So if you are using static scoping, there is no way. So the only alternative is you have to have some way of actually passing that argument, passing that variable to the from A to B, function A to B. So this is one of the needs that we have. So the way that this argument passing, the caller will call the function with an argument. This is called actual parameter to the function call. So this is the actual parameter that I have, and I send that parameter to the function or a procedure to be used as a value or whatever. So I want the callee to know about this particular variable. Okay. In the callee's case, in the definition here, that now it says, okay, this A is something that will be passed from the caller to me. And this is called a formal parameter. This argument is usually called formal parameter. And I can access this parameter in my body of in the body of this code. Now the question is, how do we actually do this thing? So there are specific questions that we can ask. First of all, when do we evaluate these parameters? This is and how do we evaluate these parameters? Meaning, this is an expression here or a variable name, and I want to actually get this from here to here, and when do I actually evaluate this I? If this is a expression, if I think that as an expression. So it could have been something like this, perhaps I plus, for example, 2, or just J, or whatever, right? So when do I evaluate this? Do I evaluate the value of I and pass it somehow? I force evaluation of I so that it has a, especially if you think about this lazy evaluation, do we force it to actually evaluate before we get into the function, before we pass the control to the function, or do we wait and do still allow this lazy evaluation to wait till, in this case, A to need this value? For example, if it is printing something, then it will need this value, and then we force the evaluation happen at that time. So when do we do this and how to do this? This is the question, first question. The second question is, how do we pass the actual parameter I to the formal parameter A? How do we do this one? How do we pass it? What do you mean by this one? There are ways of actually doing this, perhaps. What we can do is, for example, we can say the passing can be done, let's say, by just evaluating, and this will answer the first question as well, by evaluating the value of I, whatever the value is, and just pass that value to A. And for as a local A, in that case, can be treated as a local variable, and it will have a value in the beginning. But you can do other things here as well. You can say, okay, instead of doing that, you can say, okay, I can alias A and I to refer to the same memory, and other options we are gonna see. This is a very there are 4 different options that we have that we want to discuss for this particular case. And then at the very end, do we actually if there is a change to A, for example, inside here, do we reflect that change on I? This is another question that we need to ask. So how the formal parameter values are passed back to the actual parameter. This is not a return value though, be careful. So you might have an explicit return value of a function, and that will be easy. So a return is always calculating a value and returning it. Perhaps in an in a lazy evaluation scheme, this may not be the case, but return statement is something that you have there, and you know what is actually being passed back. And there are options there as well, similar to this one. But this is it's a more of a procedural or questions for procedures. Do I allow the changes that is made to A be reflected on I? Why? We said if you have a procedure, right? And procedures usually would, I mean, true definition of a procedure will not have a return type or return value and type, of course, but it needs to do something to the environment. And I don't have any parameter. So if I have a parameters that comes in, but I have no way of actually modifying something here that is reflected on the color side. So I am doing something inside. Let's say I have no way of actually modifying, let's say, I here that is that is kind of, let's say, assuming A and I are the same thing. If I don't have that possibility here, the side effect that I want to do here is very limited. I don't have a global variable. Assume that I don't have a global variable, and I cannot actually modify the actual parameter that is passed to the callee. Then what am I doing? What is this function doing? Let's say it may be doing print. That's probably the only way that it will do. But the caller may actually intend to have the side effect on its parameters, on its variables, which is its activation record, and it is, let's say, reference environment. So those variables might be, the semantic may imply that I want to change I when I call F as a procedure. So how do I actually make that happen? I need to make that happen such that when I pass I to the function F, at some point in this function, A is gonna be assigned to some certain value, let's say, and this change here, this assignment, this particular assignment here, will cause I to change so that the semantically intended side effect is going to take place. Now, how do we do this? We are going to see that there are several possibilities to actually achieve this, name the two possibilities. So let's look at those now. So depending on, so especially for the last two questions, what happens to formal parameters, actual parameters, and formal parameters? How do I actually relate them? One simple case is called pass by value. We are going to get into the details of that. Another possibility is pass or call by reference. Another one is value result. And the last one is going to be pass or call by name. So let's start with a question, a simple question. So what is the result of this particular program in a C-style program, assuming that I don't know how we are actually doing the parameter passing from actual parameter to formal parameter. So I have I and J 1 and 2 in my local, in my activation record here. I call the swap function. Swap function calls I and J. So this is I and this is J. So, and then there is a swap happening here, and then I am printing it. So if you think about this thing, the result of this is gonna depend, absolutely will depend on the parameter passing mechanism that you are employing here. So if this was C, what C is using, the answer is gonna be 1 and 2. It will print I1 and J2 because C by default uses what we call pass by value. If this was another language where, let's say, pass by reference is used, in that case, what will happen is that the answer is going to be I equals 2 and J equals 1. And we are going to see how this happens. So this is, again, the answer to this question is, if we see this as a C code, we know the answer because we know the passing mechanism employed by C. But if this is not, if we don't specify that specifically, that this is using this or that specific passing mechanism, then you cannot know the answer here. You have to understand how this relationship between or passing mechanism between your actual parameters and your formal parameters happen. All right. So pass by value is the first one. This is very simple. On the caller side, you have, this is your variable I, and then this is your binding. This is the memory. And within the memory, you have certain values kept for I, initialized or uninitialized. I don't care anyway. So something is there. So callee has its local variable. You can now think this as a local variable, a name. And the binding, memory binding to this is a different space, perhaps in stack, on stack, somewhere on the stack, and it has its own memory. And then when there is a call happening from caller to callee with this statement here, or an expression, the value within I's memory, the value, current value of I, is explicitly taken and placed verbatim in the place of A's memory. So this is very simple. This is like an assignment statement. So you can say that what we are doing here is if, the semantic of this is going to be, when I pass this thing to this guy, I have, first of all, I have something like this. The first statement that I'm going to execute is this guy, assign I to A, and then continue. This is what it means. So this is the most common one that is used as a parameter passing mechanism. Replace the formal parameters by the values of actual parameters. Formal parameters value is replaced by actual parameters value. And then actual parameter doesn't have any change. It is not going to be affected by this anymore, because after the caller, I is not going to be seen anymore. I is a local thing for this guy, unless it is defined as a global variable, which we are not assuming at this moment, or we are assuming not to be global. I cannot be accessed within this particular block of code. So that means that now I can, once I am inside this thing, this is not available to me anymore. I only have A, and I can use A to access the value of I once. And then I can actually do whatever I want here. And then when I'm done, I'm going to return. So actual parameters, there is no change. There will be no change explicitly. You cannot make any changes here. Formal parameters are going to be local variables. This is the style of C, C++, Java, and Pascal. All right, very similar. So let's say for this particular code segment, this is what's going to happen. So when I actually call this swap function here, I have I and j, my actual parameters. I have a and b here, my formal parameters, right? And then I copy the value of, I know that I is 1. I copy the value of I 1 here. And then I copy the value of j, which is 2 here. Now I have something like this. And then when I get into the code here, there is a temp. Temp says A says the temp, A is assigned to temp, B is assigned to A. So B is assigned to A, and temp is assigned to B. So in effect, what I'm doing is I'm actually changing the values here, swapping them. And then this is now the final situation after I come to the end of this code here. Now what happens here is that local A has 2, local B has 1. This was supposed to be, this was tied at the beginning to I, and this was tied in the beginning to J, but that tie after the copying is lost. And then when I return, I and J is going to stay the same. So this specific pass by value method shows you that you pass the value to the function, you make, or procedure, you make your changes there, local changes, and those local changes will never affect the actual parameters in this scheme, in this mechanism. Very simple. So if we are using this as a swap function, we know that this is not going to work. For example, in C, this is not going to work, meaning I and J will not change their values. This is clear. Now, we have discussed this when you took C programming language, like in your second semester. So what happens when we have pointers? So pointers are still, we know that, for example, if I have a function like this is a pointer, and my formal parameter is p, and the type of that formal parameter is an integer pointer. Therefore, when I actually call such a function, I know that this p is gonna actually copy, if for example, f is called with something like, let's say this, I have a local variable integer, let's say I, and I have something like this called to my function, the f. Now, p is gonna have the address of I, but P itself, so this type of, let's say, assignment can actually change the value of A. This is an implicit thing because of the pointer types. Pointer types are actually something specific, and this secondary call, or being able to actually take the address within that parameter, and actually use it for side effect, or use it for, let's say, changing wherever it is actually pointing at, is a possibility provided by some languages like C. But still, this is pass by value. We know this one. Similar thing for Java. Java will actually, in this type of with this type of a thing, will copy the object V, and when you do whatever remove all, it will actually do this on the copied object. All right. Of course, using pointers, you can achieve what, as I said, what there's a pass by value cannot do it. Whatever it cannot do it, you can achieve actually implicit, or let's say, by using the pointers, you can do side effects. But this is again, doesn't change the fact that the actual parameter and the formal parameter itself, the formal parameter itself actually doesn't change the value of the actual parameter, and so forth. So now, when you have these type of pass by value mechanisms, your caller can call the function with an expression here. This is very easy, right? So if my function f is, let's say, in this case, this guy, I can actually have an expression here. I don't need to have a variable here. I can also have an expression, but we are talking about, for the time being, not an expression here, but f is going to be called by a variable, whatever the variable is available by the caller. So just a variable name, right? When we talk about a value, pass by value, I don't need to have just a single variable here. I may have an expression here, which we usually do. Like, for example, in C, I can say, let's say, address of I plus 5, for example. This is very dangerous, but anyway. So what I'm doing here is that I'm actually sending you an address, integer address, integer pointer value, and this is the address of this guy plus 5. This is not we are interested in for the time being, even though I can use it as an expression. We are interested in this type of calls where we have just a single variable. My formal actual parameter is just a variable, and my formal parameter is, of course, a variable. All right. All right. So let's get out of these. We discussed them. Now, the second approach, the second possibility is what we call pass by reference. Okay. Let's take a 5-minute, no, let me see, a 5-minute break or 6 minutes break. We are gonna start at 11 o'clock again. See you in 6 minutes, or maybe 5 minutes, 6 or 5. Okay. Okay, so the second possibility is using what we call pass by reference. Caller will have a variable as its actual parameter, right? And the callee will have the formal parameter, A. And what happens in this mechanism is simply the A is bound to this actual formal parameter A is bound to the same memory as I. It's like an alias, right? This is called aliasing. So the formal parameter becomes alias of actual parameters. And any change that we do on the formal parameters will be reflected, of course, on the actual parameters. So Fortran does this, and C++ reference types and Pascal variable type, var type, is actually is using this type of mechanism. In this case, now you can see that this is like C++ syntax, which achieves this. Again, it's kind of a implicit. This is kind of explicitly saying that this is a call by reference, because C uses not just one or C++ doesn't use just one mechanism. It uses several different mechanisms for passing, or at least two mechanisms for passing values to procedures or functions. And this particular one is actually specified this way, the interface. And then once you have this one, you know that for this function, you have when you call the function, when the main caller main calls the callee at this line here with I and j, it has its I and j variables, and then in the same order, A is alias to I, and B is alias to j. Now, A and B and I and j are the same things. The names are different, but they are actually bound to the same, at least memory, right? And then now what I can do is, in this case, when I actually do this type of a change here, using this temp, and you see that 1 and 2, when they are exchanged, then I and j also see those changes. All right, so very simple. Okay, you can achieve this with C, of course, using pointers, but they are not the same thing. So C is still using pass by value, and that's it. Okay. So some languages go a little bit. So some languages say, okay, you know, the reason that I may want to actually use this this particular passing mechanism from let's say caller to callee might be actually, in general, might be actually for changing or be able to reflect the or do side effects, right? This might be one possibility. I mean, and this is a reasonable possibility. And we said, okay, this is one of the reasons that we actually want to have these type of mechanisms. Another advantage of this mechanism is actually the calling and the caller and callee. The amount of operations that you do in this case is just the aliasing operation. So your formal parameter just is alias to your actual parameter, and that's it. That's the mechanism to actually associate your parameters with each other, and then done. And then the rest of it is actually is whatever the code that you have here. Now, this means that your overhead for making this value passing is actually, even just one way from caller to callee, is minimized, meaning whatever this aliasing procedure is actually going to require, however many computer or CPU cycle it will require, perhaps a few copying operation, but just address copying operation, maybe 1 or 2 or maybe 3, I don't know, doesn't matter. But the overhead is almost minimum compared to copying the entire content of I to A explicitly in memory. So assuming that, for example, I is an object which has, I don't know, let's say a megabyte of data in it, then you need to actually copy that megabyte of data from I to A. So this is a big overhead. So one of the advantage of pass by reference is the overhead of copying this passing operation will require some overhead. This is clear, but this can be minimized by pass by reference method, especially compared to pass by value. So this is one advantage. Of course, the other advantage is, again, if you need to actually pass the value back or induce side effect, then this is the only way anyway, or at least there is no way that you can achieve for that with pass by value. This is one way of actually achieving that. Of course, this is quite dangerous. If this is your only mechanism to work with, and now the question is, what if I don't want f to make a change to my variable? I don't want it to change. I just want it to pass the value and operate on it, and then return me something. For example, if this is a function, I don't want I to be my actual parameter to be actually modified, and I don't know how it is going to be modified by your function. So this is that software engineering part of the thing that actually I want to I want to make sure that you are not messing my stuff up as far as this function is concerned. Now, for that, some languages say, okay, maybe what we need to do is we need to actually have an intermediate mechanism, some other mechanisms to actually let optionally turn this off. I want to pass it one way. I want to send something to you one way. You are going to be aliasing it. You are going to be using it, but I want to make sure that you are not changing it. You are not reassigning something to it. So this is in C++, for example, is achieved by this construct. So this const probably means constant or don't change it. So in this case, this type of thing kind of gives us an option, and some languages do this, option saying that, okay, once you have a definition on your function saying that it has a const there, this means that you are never going to be able to actually, within that function interface, specification interface, if it includes a const definition, const in that formal parameter definition, then you are not going to be able to make an assignment to P. That's what it says. All right. So once you have const here in this example, P assigned 0, assigning 0 to P is going to cause an error during completion. Right? So this will say, okay, you said, your interface specification says P is doing a reference, pass by reference, but it is doing it only one way, from caller to callee, not the other way around. So that means that within the body of your code, you can never ever change P. You have to keep P without an assignment. So you cannot touch assignment. You cannot touch P or write on P. You can read it, but you cannot write it. So this is kind of a deviation from the basic idea of that. So advantages, yes, it may provide as an advantage that I can rely on your function a little bit better. The disadvantage is actually this is an exception. I mean, this is an additional rule that you need to actually be aware of. All right. Third option. Third option is actually kind of a way between these first two. So instead of aliasing, so some people, I mean, some will think that, okay, aliasing is a dangerous thing because whatever I do to my A when I alias them, like this here, whatever I do to A is gonna be directly reflected by I. This is a very, let's say, how do I say, liberal use of, is a very liberal use of side effect. The effect is gonna be instantaneous, meaning if I have, let's say, multiple lines of code here, let's say that statements, I have this many statements in F, and A is actually changed here, assigned something to A here. At this line, this is the first line, the second line. The second line of code, when it actually reaches, executes the statement, A is gonna be changed. And that change is gonna be directly reflected on I right over here. Okay, so what is wrong with this one? There are possible things that may go wrong here. So one possibility is that, first of all, if you have an exception, right? Let's say at this line, after this line, at the line 3, you had an exception. And when you throw an exception, when you go handle the exception, now it may not be possible to know where that exception is coming from. Did I already do the line 3, 2? Did I have already, let's say, a modification on my actual parameters? So let's say an exception that I have here and an exception that I have here will mean two different things as far as what the recovery is going to be. If you are talking about resumption, you want to resume where you left off. So this type of a thing will complicate the behavior of exceptions. This is clear, right? This is one thing. What I have actually preferred is, in this case, for example, let's actually do the side effect at the very end. Why am I doing the side effect in the middle of the code? Let us wait till the end of the function. Everything is completed, and when I return, I do the changes. Now, from the perspective of program, from the caller will get its side effect, desired side effect. So from caller's perspective, nothing has changed. But from, let's say, exception handling or some other problems that I'm going to discuss in a few minutes, the handling of callee's abnormal behavior could be simplified. So will be simplified. I know that if something happens before return, I haven't done anything so far to actually change something on the caller. Therefore, for example, from a resuming from a exception might be easier, much easier to handle than if I don't do it that way. Another possibility is that I might have, for example, I might want to use this for parallel programming or, let's say, distributed programming. I may want to actually give, let's say, I might have another function G here that actually takes J here, and or maybe the same function, right? I may want to actually, let's say, if I have something in terms of concurrency here, I may want to actually send fi function to one CPU, and GI or GJ function, FJ function to another CPU. And whenever they are done, I can wait here. And whenever both of are done, then I can resume my thing. Now, this means that the effect of Fi and Fj, especially on this, maybe the same thing here, same value, is not gonna be, let's say, reflected in the middle, but at the very end. All right. So for this one, this is the mechanism. This is called pass by value result. This is a very simple thing. What you do is you do as if you are actually doing a pass by value first, and then at the end of the program or at the end of the function when it returns, just before it returns the control to the caller, you actually copy the results back to the actual parameter. So take the actual parameter, the value of actual parameter, copy it to the formal parameter, and then whatever you have done to that formal parameter, whatever that formal parameter has, and copy it back to your actual parameter, corresponding actual parameter. Now, again, this has that advantage of actually abnormalities that we discussed that what we actually handle. But of course, with the cost of 2 copying operations, the overhead is going to be maximum here. Okay, so very simple one. You can see that this is going to work. You will copy 1 and 2 to A and B, and then you will replace them 2 and 1, or you will swap them. And then once you swap them, at the end of the code, the A and B will be copied. The values of A and B will be copied to A and J explicitly or implicitly. You don't need to do that, but it will happen. Now you actually achieve the same thing. Again, the advantage is you are not going to do the changes when you do the aliasing. You are going to do the changes in the middle of the code. This will guarantee that the changes are going to be done only at the very end of that procedural function. Of course, there could be unspecified issues here, very simple issues, like, for example, this one. You have function f that takes A and B, and then you have you call it with the same formal parameter. So actual parameter. So you call A and B with the same actual parameter. Now the question is, so going this way is easy. So you'll be copying this one first, and then this one second. This is fine. The first one is easy, but the second one, when you get out of the function, copying it back is going to be more difficult. Then you don't know which order it's going to happen and so forth. So this will be when if I do the 1 and then 2 A and B in this order, let's say maybe I do it in this order, then it will have 2. But if I do this random ordering or the other way, this way, then I will have a 1 here. So these have to be somehow handled. You can perhaps do this one, handle these by, let's say, checking that you shouldn't actually pass the same parameter, or you can let this be handled by the programmer. Programmer should know about this. But these are quite a bit difficult things that these type of possible errors in semantic is very dangerous. Programming languages people don't like this, or designers don't like these type of things, because I need to be, as a programmer, I need to be aware of this one. And as the number of things increases in numbers, number of things increases of these type of exceptions or possibilities, problems, then my capacity to hold them in my brain during my programming will actually be reduced as those number increases. Okay, the last one. The last one is called pass by name. The idea is here is this. It says, okay, I have my actual parameters, and they are evaluated only when they are needed. This is kind of following this lazy evaluation concept of expressions, but in this case, not expressions, but the values, the variables. So this idea is if I pass you I as a parameter, as an actual parameter, now A has this parameter, but it doesn't evaluate it. So this is not pass by value. But it's not also just a simple pass by reference or pass by value result, because I don't want A to be actually having a side effect on my I. Okay, so the same parameter can be evaluated multiple times. Evaluation is evaluated in the calling environment. The callee can change the values of variables used in argument expressions and change the expression's value. So this is again a solution for parameter passing for normal order or lazy evaluation, not strict evaluation, lazy evaluation. So very few languages have this because of the implementation difficulty. This is a very, very difficult thing to implement. We're gonna see a few examples in a few minutes. And it's not adopted by major languages because of, again, the implementation difficulty. So let's go back to this evaluation strategies that we discussed before. Strict evaluation is the arguments to a function are always evaluated completely before the function is applied. This is either the pass by value requires this for sure, because I need a value in I to be there. And it's called also eager evaluation, right? Non-strict evaluation is I have an assignment to a variable, let's say, okay? And this variable, when it is used as an argument to a function, they are not evaluated unless they are actually used in the evaluation of the function body. In a function body, if there is a need for evaluation, let's say like printing, then I actually do this one. I evaluate this. So this is examples of this is actually short circuit or lazy evaluation. So if you recall this applicative order and normal order thing, we had two different types. In the applicative order is a strict evaluation. The arguments of a function are evaluated from left to right. So this is also defining how to actually do this thing. So if I have arguments, actual parameters to a function, when I do this one, applicative order says, okay, start from left to right, evaluate each of them, make sure that those variables have, or the actual parameters have all values in them now. Their values are defined. And then call by value, in this case, the argument expression is evaluated and the result is actually a value is bound to the corresponding variable in the function, the formal parameter. Call by reference, a function receives an implicit reference to a variable used as argument. Okay. Call by sharing, different from call by reference in that assignments to function arguments within the function are not visible to the caller. Call by value result, we discussed this one. In the non-strict case, when we don't have a lazy evaluation or a normal order evaluation, so the outermost reducible expression is always reduced in the parameters, in the formal parameters, applying functions before evaluating function arguments. So this is only, if you recall the definition, we start from outermost and go to the this is like a top-down evaluation versus a bottom-up evaluation of an expression tree. In the call by name case, the arguments to a function are not evaluated before the function is called. They are substituted and directly into the function body and then left to be evaluated whenever they appear in the function. This means that if I am actually doing a non-strict evaluation or normal order evaluation, when I actually pass something, some parameter to which is actually not evaluated, some expression, let's say, which is not evaluated to a value, I copy the entire expression to the formal parameter and then only evaluate it when I need it. Okay, so this is at least conceptually simple. So let's look at this example here. I have the same code and I'm going to assume that I'm going to use pass by name. So what happens is that when I actually call it by ing, it will pass the name I to A as a expression, and it will pass also J as a for B. Okay, so like here, I is going to have A is going to have I as a expression and B J as an expression. And then when I actually do this temp assignment, I have to evaluate I. This one I have to evaluate now. Assignment requires an evaluation. It forces evaluation because I cannot copy it otherwise. So then one is copied here. And then when I actually do this copying from A to B, B to A, then I have to evaluate J here, which is 2. And then I would actually put that in there. And then, of course, temp is already evaluated. So when I actually put back that, it will be changed. But you can see that this is not going to actually reflect anything on ing, right? Okay. So now of course, this pass by name again is a concept wise it can be, or it is useful in true functional programming languages, but implementation could be very, very difficult. And especially, so there are two things that you can actually think of here. So if my formal parameters or actual parameters are just my variables, then you just actually push the name in there. And then that name is copied with its content, and it is evaluated whenever it is needed. So this is simple. But in some other cases, perhaps you can actually put here, or I might have. I mean, in this case, when there is an assignment, there will be always forced to evaluate. But if I am doing, let's say, if I am able to actually pass here expressions, like let's say I plus J, then things become, of course, more complicated. I need to be able to maintain this expression and copy it to A. Here, A now actually having this I plus J, perhaps let's say the second one is 2 times J, let's say, and then B is gonna be retaining 2 times J. And then only when I actually have a statement that requires this specific forcing of actually forcing to be evaluated, then I do it. Of course, if this is in a context of a programming language, we know that no function will have side effect. So this means that when there is no side effect, that means that there is no either print or assignment operator in the code. Therefore, you are not going to be forcing the operation to take place. Now, in that case, your function calls, especially if you have, let's say, nested function calls, or you have recursive function calls, the tracking of these names will become very, very complicated. So your function could be, for example, you have an integer function and it has two variables. I'm not gonna worry about the type of those. And perhaps you are returning, let's say, just simply a plus b, for example, right? Something like this. Now, if I call this one with I and j, I need to actually say, okay, I am returning at the end here I plus j. And the question is, when do I wanna actually evaluate this thing? Do I retain this in my, let's say, as an expression, a return type, and only enforce it at the end and so forth? And then the other question, of course, is what is the value of I and j? If I return it this way, then I come back, let's say in my code, I have integer, let's say I and j, and I have some, let's say, things I have done. And now I am calling, let's say, I plus f of I and j. Now, pass by name tells me that fij, I and j here, a plus b, it is going to be I plus j. So the semantic of this thing is going to be I plus j, right? Now, of course, now the question is, what if, I mean, when there is no side effect, I don't care because nothing has changed I and j. So whenever I evaluate this, I am going to get the same thing. But if I have a, let's say, in between, let's say, if I had a side effect somewhere, then I cannot actually keep this particular thing as a around and evaluate this only when I need it. So when there is no side effect, it doesn't matter if I actually do the evaluation here and return the result. Let's say I don't know, maybe I was 1 and j was 2. And so this will mean that actually 1 plus 2, 3. And then I will add 1 to that one. That will be 4, right? So this effect. Now I can do it here and then add to that I, or I can actually keep this entire thing like this and do it only somewhere that I need, maybe wherever I use this one. I would only use evaluate it when I need the value. If I'm doing an assignment, for example, right now here, then I can say, okay, now I need to actually evaluate this thing. So in a normal order evaluation, if your language is actually truly implementing a normal order evaluation, these type of things are not difficult because there will be no side effect, and therefore when there is no side effect, you can actually retain these things. Now the question, of course, is if, let's say, if this is a parameter, it's not going to be a parameter to that thing, but anyway, so you can actually keep it this way. Now the question is, as you have, let's say, functions that are, let's say, that could be, let's say, called in a composite manner many, many times, these expressions can become quite, let's say, complicated. So the implementation difficulty comes from there. But the idea is very, very good because I don't want to, perhaps at some point in my code here, maybe I'm not going to actually need this thing to be evaluated. And the evaluation is always expensive. Evaluation means do certain things, get the values, and maybe those, let's say, if you are doing very, very expensive calculations, you may avoid these calculations at the end of the thing. Maybe you don't need it. You find out that, okay, there is an alternative to do it, and that alternative path takes place rather than this path. So idea is a very good one, but implementation can be quite difficult. And some algo, I think algo 6 or whatever, has some implementation of this one, but not all of it. Okay. All right. So That's there is something here. Could you please explain the problem with pass by reference when we have an exception in the following lines of code? Okay, so let's do that one first, and then what time is it? Okay, we have 15 minutes. We have time. So if you recall, we said, I think he's talking about this one here, right? So we said the difference between call by reference and value result, pass by or call by value result, is this end effect are the same. Both will have the same end effect. But the way that within the callee, in one case, in the call by reference case, whenever the callee actually modifies one of its formal parameters, it will be reflected directly on the caller side, and that actual parameter is going to be actually changed. So in the other case, in the value result case, the change is going to happen. The actual semantic is going to be the same, whatever the change. For example, if I is going to become 10, it's going to become 10, but it will be only done at the very end of the function call. Okay, now think about this function to be having, let's say, 1, 2, 3, 4 lines of code. So let's say that here I am actually assigning a something, whatever it is, and then I'm continuing with this one. All right. So this is the second statement in the callee is my my side effect. So this means that in particular, of course, this guy means that at this stage, so at this stage, I am gonna change I to be whatever this thing is, right? This is what it means. So let's call this one line A, B, and C. And these, within this, I have 1, 2, 3, 4. So the flow of control is gonna happen this way. A is gonna be done first, and then B is gonna be done. Within B, this is what's gonna happen. 1 is gonna be done, 2 is gonna be done, 3 is gonna be done, right? And this is 3. And 4 is going to be done, and then C is going to be done. Oh. Let's do this one a little bit better. Okay, 4 and 4. This was right. Come on. So this is parentheses. This is the parentheses, and C is going to be done. This is the flow of control. Execute A, this line. Execute B, this line. When we do this one, control goes to callee. And it will execute line 1, 2, 3, 4 here. These are the line 1, 2, 3, 4. And then once it returns, it will return to C. All right, so this is very simple. Now, if I am doing this, let's say that for some reason, this guy can throw an exception. Will throw an exception. All right. So assume that in one of those lines, especially after line 2 executed, maybe say here. At this stage here somewhere, I can have an exception. Now, so this means that the exception is going to happen, let's say here. There is an exception here. So this means that now I need to change the flow of control. I'll go to my exception handler. Now, let's look at the exception handler. Exception handler, and what we want to do is we want to assume that exception handler should recover from this situation somehow. I don't know what that means. Now, from exception handler's perspective at line 3 or 4, when I actually have a, since I executed already line 2, sorry, in the callee, the value of I also has changed, right? So the value of I has changed. Now, if I want to undo the changes of this function and return as if this function has not been called, what do I need to do? I need to change the i's value to original value or a's value to original value. So this is a kind of a, now when I change a's value to original value, I will be reflected, but depending on where this exception is actually is generated, I may or may not know actually what happened. It may be that actually the exception happened before 2, and I don't know if A has been changed. So I need to keep track of these things. So I cannot just say, okay, bail out here. If I bail out, it may be that A may have been changed, therefore I is changed, and I cannot bail out because you changed my I. I mean, you changed my variable I to call from the caller's perspective. So this is not a bailing out. I mean, you are bailing out, but without handling side effects. Whereas I can say, okay, if it happened before this assignment, I can bail out easily. But after this assignment, I cannot bail out easily. I have to actually undo the things. So this means that my handler, exception handler, has to know the situation and resume the situation or handle the situation so that it can actually do the thing. Now, if it even knows that A actually has changed, the handler may not know what the A's original value was, right? It doesn't have any idea what it was. So this is a difficulty to, I mean, once actually the thing happens after the assignment, the handler has no way of actually undoing things because the effect of A changing value, any change on A's value is reflected on I's value. And I cannot say, okay, I haven't called this function, bail out this function and try again, maybe, I don't know. I cannot say that anymore. However, if this was a value result call by value result mechanism, I know that A's change doesn't reflect, is not reflected on I yet. So at the end, wherever this thing happens, this exception happens, I can just ignore it. I can say my caller, let's say on this side, I can say, hey, you called FI gave me an exception, and I'm just bailing out. Meaning the caller now knows that its internal state has not changed. Nobody has touched its internal state. So it can say, okay, I'm just okay, continuing from here as if nothing happened. Or whatever the semantic that it actually wants to add, it can do that. And that could be only possible with a value result mechanism, because value result mechanism hasn't updated I and J, or in this case I, till the function exits. Of course, if the exception happens during the exit, which I am not assuming exception is going to be caused by an expression, evaluation of an expression, or execution of a statement. It's not going to happen out of the blue for whatever the purpose is. So this is one advantage that this might have. Other advantages may come when you have, let's say, multiple, when you have concurrency, that you actually take the function and evaluate it twice. I mean, let's say, evaluate multiple functions at the same time, so that their results doesn't confuse each other. If you have a side effect with a call by reference, then you may actually not know what's going to happen. But in this case, if I call FI twice, I know that the original value is going to be whatever the I has at that time, it will actually go and actually do it, and then return was is going to be reflected. So there is nothing going to be happening, or uncertainty is not going to happen within the callee itself. So this is the main advantage of this method. So let's look at a quick comparison of these method. Call by value. First of all, it is efficient in terms of referencing, right? So you just copy a value. You don't need to go for a indirect reference, referencing, and so forth. So this is very simple. I have an integer. I take the value, copy the value, and then I'm done. However many times I am going to access it, I'm not going to actually go to an address and then from that address to the actual value, right? So this is fine. Of course, inefficiency if the value is very, very big in terms of size. So if I am, let's say, having an array or a set, which has, let's say, my value is a set of 10 entries, I need to copy 10 entries, 10, let's say, integers for each call, and this could be expensive, right? So the downside of call by value, another downside is actually flexibility. So if you don't have a pointer, again, you cannot avoid these type of copying operations, and it is less flexible. You cannot actually, without pointer, you cannot ever modify something back on the caller, right? So then you need to actually be careful with how you handle arrays, structs, and union as parameters. You have to be careful with those. Call by reference, it requires one additional level of indirection, which is probably not a big deal if the copying operations are say, out of an issue. So again, this additional indirection, level of indirection, has been an issue in the past because the values were kind of small, addresses were a little bit larger, and when you compare these, it might have actually, it is now different. These days, because of memory is abundant, people tend to actually, the values tend to be larger in size, in memory size. So 64-bit, let's say, integers or double numbers are more common these days than, let's say, in the earlier days. So when you actually talk about the indirection, let's say 20 years ago, you were doing maybe 16-bit operations, copying 16-bit versus if your address space is 32-bit, then 16, or even if it is 16-bit address space and 16-bit values, then 16-bit is copied once and actually you go over that, versus you go for a 16-bit value, put it in a register to get to the address and then get to the address's value. So it will require 32 bits, 2 times 16-bit operations. Whereas these days, what happens is that values are actually larger. So 64-bit, let's say, types are much more common than, and address space is usually either half of it, 32-bit, or maybe at the same level. So because of that, the difference in this of this indirection is not a big deal anymore. And another thing is that hardware designers actually know this trend, and they have actually made their caching mechanisms more favorable to these type of interactions. Therefore, the speed that actually you lose is not a big deal usually with the modern architectures. If a parameter is not a variable, a constant, and memory space must be allocated for it. For example, and another thing is that if you are passing, let's say, this to your pass by reference. Now, this guy is a constant, is a literal. It doesn't have a memory. It's not specifically put in memory of the same format. So what needs to be done is there will be a temporary variable created, and this temporary variable is going to have this address, and 12 is going to be put in here, and then your formal parameter A is going to be aliasing to this guy. So there will be, for these type of things, there will be quite a bit of overhead, creating of this thing, binding the entire stuff, and then aliasing it is going to be expensive. And of course, at the same time, this is very, very simple to implement, very easy to implement. Call by value result. You may not want to change the actual parameters during the when facing exceptions, especially. Right, so this is the only advantage of this one. This is very, very inefficient, of course. You copy it once, and then when you are done, you copy it back. Those copying operations are going to actually be expensive. Call by name supports lazy evaluation. It is very difficult to implement, and the advantages is still, let's say, debated. So ardent fans of, let's say, functional programming will go for these type of things, but not necessarily, let's say, practical. In practice, again, C, as we can see, Java and C++ actually took over most of the programming things, maybe Python as well, and they all support these call by value and call by referencing, and call by name is not actually implemented because of the difficulty and also the conceptual differences between imperative versus functional programming paradigms. So this is about it for, we are already 1 minute over anyway, for procedure or function calling mechanisms. Any questions? Okay, if there are no questions, then I will stop the recording. And next week, we are gonna